Welcome to another edition of RCE. Again, I'm your host, Brock Palin, and you can find me on Twitter at Brock Palin, all one word. And you can find the show online where you can find all the back shows at www.rce-cast.com. And also, there was an issue with the iTunes feed where a bunch of shows were missing. That is now fixed, so those of you who are looking in the iTunes catalog and it looked like we hadn't updated a show in a long time, they should all be populated now.
Yeah, we're going to blame that on the RCE gremlins. They appear every once in a while, but this one was definitely their fault.
Yep, and that is my co-host, Jeff Squires from Cisco Systems, and also one of the authors of OpenMPI. So, Jeff, thanks again for taking some time out of your busy day.
Sure. And I got to throw in the obligatory ping from my blog out there. Get to it from the RCE webcast. It's on blogs.cisco.com. And I just write about general MPI, HPC, networking kinds of things. So please feel free to drop by and send me your thoughts. So, okay. Brock, what are we doing today?
Today we're talking about XDMF. It's kind of like a file format, but it uses guests we've had on here before for actually storing a lot of the data. So I need some clarification of exactly what this is. So I'll go ahead and introduce our guest instead of hacking up exactly what it is. Our guest today is Jerry Clarke, who is from Army Research Laboratory, and they were kind enough to let him speak with us about this. So, Jerry, why don't you take a minute to introduce yourself and give us your background?
Okay, sure. Hey, Jeff, Brock. My name is Jerry Clarke. I'm from the Army Research Laboratory. I work in a Computational Science and Engineering Branch. And what we do, I don't know if you know a lot about the Army Research Laboratory, but it's the cutting edge of a lot of basic and applied research. And to help the soldiers is what we're really after. And we do a lot of analysis and design, which is inherently multidisciplinary. So we do a lot of things like computational structural mechanics, fluid mechanics, multi-scale physics types of things. And what we're trying to do is we're trying to avoid the stovepipes that regularly occur, and not only in those disciplines, but in codes in specific. In other words, a single code may have its own preprocessor, its own visualization system, and it just got ridiculous after a while. So what we're looking for was initially just a common data model and format that we could use for visualization and preprocessing over multi-disciplines. So we didn't find anything that perfectly suited us out there, so we decided to develop our own. And what we came up with, it's called the eXtensible Data Model and Format, XDMF. I guess it could have been eDMF, but EDMF didn't sound right. So we went with XDMF. And it's a lot of different layers. I guess it's like Shrek said, it's like an onion. A lot of different layers. On the top layer, it's just a common data model and format. Uses HDF5 and XML, and if you use that, you can pull it into a lot of visualization packages, and you're off from there. If you want to go further into it, you can use it to couple codes and do a lot of other things.
The interesting thing about XDMF is Kitware is involved with this somehow, who we've had on this show before. What exactly is the relationship between you guys and Kitware?
We have a very long history with Kitware. We were involved in Paraview from the very beginning, and that developed from our interest in VTK in general. So as XDMF was developed, one of the first things we needed was a reader in Paraview. So we worked with them there, and they kind of got a little more interested in XDMF and helped contribute and helped get the word out there a little bit for the types of things it could be used for. And it just sort of snowballed and rolled from there.
Cool. So let me go in on part of what you said earlier. You said none of the existing systems out there did what you need, and so you went and rolled your own. So what kind of features were you looking for that others don't support? So what are the unique attributes of XDMF?
Well, we needed something that was platform independent. And we had used HDF before, and a lot of the systems that were in development at that time, I'm thinking particularly of DOE's SAFE and HDF EOS. They were using HDF as well. So HDF was pretty much the way to go, it seemed, for cross-platform data format. But then to describe the data model, what types of things are in there, what is my topology, what are the names of my scalars, and things like that. there were a lot of very complicated systems. We wanted something, I guess, more would be described as a data catalog than a data model and format if you're a purist about it. But we needed something easy to do easy things. And we came up, and that's why we came up with XDMF. We use XML because it's easy to parse. It's easy to dig down into the guts of it and see what's going on. And we use HDF5 because it gives us cross-platform platform independence, and it gives us good high performance in both scalar and parallel applications.
All right, great. So that actually leads straight into my next question. What kind of platforms do you run on? And I was going to say, do you run serial and parallel, but apparently you do. Could you give any insight on that?
Yes, we, like I said, the first part was make it easy to do easy things. So we attacked, serial machines. At the time, a lot of SGI, a lot of Sun. Right now, XDMF pretty much runs on everything. Runs on Windows, runs on Macs. On the parallel systems, part of the Army Research Laboratory has a distributed shared resource center where we have, machines with thousands of cores, parallel file systems, things like that. So XDMF has to run there for the types of codes that we're interested in, SHOTs, physics codes, multi-scale codes. So it is particularly designed to work in those situations. I was mentioning layers before. An interesting part about that is built into XDMF is a distributed shared memory system. So you can use this in your code to make it look like your code is writing to a common data model and format as a file system, but what it's actually doing is writing into a distributed shared memory system. Not only does this allow you to do runtime visualization on a code, but it also lets you couple codes from a global perspective, as in each parallel code does not have to be cognizant of the decomposition of the other code, which gives us a lot of interesting capabilities.
Well, that is kind of cool. So do you a natural follow-on to this then is, how do you foresee this scaling into the massively multi-core kinds of environments? Because one of the issues that server vendors like myself are looking into is, how do we, accommodate the changing landscape of having a whole pile of cores inside one box rather than what customers have typically been doing in the past is buying lots of systems to get lots of processors. Now it's all in one box. Does your system kind of accommodate the change in communication architecture that's going to be required to do shared memory kinds of communication and NUMA kinds of communication rather than network-based kind of communication, or even more complicated, the combination of both, the NU-NA, so to speak, non-uniform network architecture in the box and out of the box? That was a long question.
That was a long question. As luck would have it, part of my branch is also looking into what we call advanced computing for tactical situations. And that involves a lot of looking at FPGAs and cell processors. Where we're really concentrated on there, we're getting a lot of speed up is GPU calculations. So that's been going on for a couple of years, and we have a good experience with that. So what we've used XDMF for is to use that distributed shared memory to couple both the multi-core calculations and calculations on several different GPUs. So we can use this distributed memory concept to allow the GPUs, to do their thing, to take care of their hierarchical memory, and then write into the distributed shared memory system along with the multi-core systems as well, which lets there be one spot where you can grab the data, where everybody can get to it, and it's all synced up. So the DSM is smart enough to know that if that section of distributed shared memory that is being handled by a core lives on that processor, obviously doesn't send a message, it's smart enough to do a shared memory write. But if it has to go off processor to get something, that's smart enough to know, where that piece of memory is. The shared memory system itself, is byte addressable. The neat part about it is that we've developed an HDF5 driver that sits on top of that shared memory system. So your code itself can use the HDF5 API to write into the distributed shared memory system, as opposed to using, puts and gets